Okay, we're going to try a lecture on Z-transforms. This is Chapter 5. This will be the first part of Chapter 5 that we'll talk about in this particular lecture. We'll introduce the bilateral Z-transform. We'll look at the bilateral Z-transform and compare it a little bit with the bilateral Laplace transform, see how they compare, see what's similar, see what's different. We'll do a few examples of computing the bilateral Z-transform, take a couple signals, see how that shakes out. Those particular examples will also help me emphasize why we need a region of convergence to be included in how we compute that bilateral Z-transform. All of this is very, very similar to what we did for the Laplace transform. We're going to take a very similar approach in how we motivate things and derive things and move it forward. So let's go ahead and get started. I'm going to take a look at an everlasting exponential. So this is a discrete time everlasting exponential, z to the n. If I went ahead and wrote z in a polar form, I would have r e to the j, and we're going to use a cap omega here. Then I'm going to raise that to the n, just a slightly different form, completely equivalent. Z is our complex frequency. If I write that in polar form, that r e to the j omega, I can expand this out to be an r to the n e to the j omega n. That r factor, so if I take a look at the parameter r there sitting in that first part, that's a damping factor, or what's called the damping factor. The damping factor r tells me whether this exponential grows, decays, or just sits there and oscillates. If the magnitude of r is greater than 1, it's growing. If the magnitude of r is less than 1, it's decaying. And if the magnitude of r is equal to 1, that could be anywhere out on the unit circle, then the z to the n is just oscillating. The e to the j omega is what determines that oscillatory component. And so if I take a look at that frequency variable in there, we have a cap omega. So cap omega is what I'm going to call digital frequency here, a digital frequency parameter. And we'll look a little more at this later. A digital frequency tells me the rate at which things oscillate, that they vary. The units on this guy is radians per sample. So we have radians per sample as the unit on that. You might recall that in continuous time, our damping factor was that parameter sigma, and the frequency was little omega, and that was in radians per second. So we're going to go ahead and take this everlasting exponential, z to the n, and I'm going to go ahead and feed it into my linear time invariant discrete system. So we'll go ahead and draw that system up here. So I have a linear time invariant discrete system, and we're going to generate an output. So we did say that my input, we do have this input, x of n, is that everlasting exponential z to the n, and we're going to be taking a look at what is my output y of n. From Chapter 3, we know that a linear time invariant discrete system has the output as just being the input x of n, and it's going to get convolved with the unit impulse response h of n, something along those lines. I'd like to go ahead and do some expansion on this, so let's go ahead and just write it out below. Y of n is going to be equal to, if I use the convolution sum by definition, this is a sum. We'll do a sum on k going from minus infinity to infinity. We have two arguments in there. One's left alone and one is flip and shift as a function of that sum variable k. It's our choice which one we want to do. We know that we can choose to flip and shift either of the two. In this particular case, I'm going to flip and shift x, which means I'm going to leave h alone. So I'm going to have h of k, and then I'm going to have x of n minus k. If I go ahead and plug in what is x of n minus k, I can get a summation minus infinity to infinity, still have that h of k left alone, but my x is just z raised to the, and the argument here is n minus k. So I get a pretty simple form here. If I take a little bit of a look at this guy, we can notice in this particular case that the z to the n, so I've got this little n part here, right, can be brought out as a separate term, and then I would be left with the z to the minus k afterwards. So I'm going to go ahead and pull out the z to the n term here. That's just using the properties of exponentials and the fact that it is not a function of the sum variable. So I have z to the n, sum k going from minus infinity to infinity, and I'm left in here with my h of k, and I have a z to the minus k. Getting really close to the form that we want to do here. If I take a look at this piece over here, this thing I put a bracket under, I can call it something. I'm going to call it h of z. We'll notice that that entire thing that is bracketed is a function, right, of the frequency variable z, but not a function of the independent variable n. And so When I go back to what we were starting to do, we had this input x of n, and it was equal to this everlasting exponential z of n. We were going to run this into a system. That system was going to generate an output, that output y of n. Turns out to have all of its time dependence. Looks exactly like the input. It looks like that z to the n again. It just gets multiplied by a complex constant that depends on that frequency, that h of z. So beautiful result, right? Linear time invariant discrete system. You put an everlasting exponential z to the n in, you get the same everlasting exponential z to the n out, right? But then it is modified in gain and phase through this complex constant that depends on the frequency, h of z. That h of z is also going to be called the transfer function, just like we saw in continuous time. In fact, it might be worth taking a look just really quick at what the continuous time result was like. We had a time domain signal that was also an everlasting exponential. Little different form there. We used e to the st, just mathematical convenience again. We ran that into our linear time invariant continuous system. So we had a linear time invariant continuous system, and it generated its output, also solved using convolution. And when you went through that exercise, we ended up getting back out e to the st, the exact same form as the input, multiplied by the transfer function h of s. So this is a nice result, very similar to what we'd seen before. Everlasting exponential going into our continuous time system. We get the same everlasting exponential out, just getting multiplied by a complex constant h of s. Take a look at these guys. You'll notice that the discrete time case, right, and the continuous time case are identical in form. Everlasting exponential in, everlasting exponential out, multiplied by a complex constant that depends on the frequency of the input. So let's take a little bit deeper look at this h of z. We'd already seen what that was. It's a summation. I'm going to do a sum now on n, just make it conform a little bit more with the normal notation. Doesn't matter what we call the sum variable. This just is more standard. So I'm going to do it on n rather than k. And so what goes inside is not going to be h of k, it's going to be h of n, and not z to the minus k, it's going to be z to the minus n, just changing variable, letting k go to n, something along those lines. That complex constant, h of z, right, is a summation, n going from minus infinity to infinity, little h of n, z to the minus n. I'm going to go ahead and box this. This is actually the result that we were trying to work our way to. This particular one here is the bilateral. This is the bilateral, what is called the bilateral z transform. Very, very similar in structure and in purpose to what we saw with the bilateral Laplace transform. It does take a time domain signal. So here's a time domain signal. Time domain signal in this case, we're looking at the signal h of n, but we have this time domain signal, h of n, and this transform basically takes that and converts it to a frequency domain signal, right? That h of z is a function of the frequency variable z, not a function of the time variable. So we go from a time domain expression, right? We have a time domain expression on the right-hand side, and we go through this transform, and it ends up giving me a frequency domain. So it's a time to frequency transformation. This bilateral z transform gets rid of the time variable, and it moves us into the frequency domain, this z domain, as we would call it. So if I compare that again to the Laplace transform, if you remember back from chapter 4, we had the Laplace transform h of s, right? And it was an integral. We had an integral from minus infinity to infinity. We had our h of t, and we had an e to the minus st, something along those lines. If you take a look at these guys, very, very similar, right? So we ended up in this particular case taking a time domain signal, and through the Laplace transform, it converted it to a frequency domain signal, h of s. Structure is very similar. In the continuous time case, we ended up having a integral rather than a summation, as we saw in the discrete time. That's just reflective of the difference between discrete time and continuous time signals. And it's still a signal getting weighted by an exponential, getting summed up or integrated up to give me my transform domain. Virtually identical in structure. The only differences are really those differences we'd expect in going from a continuous time signal to a discrete time signal. So this bilateral transform that we have, this bilateral z transform, we'll go ahead and write it again. So h of z is being equal to a summation n equals minus infinity to infinity of some h of n z to the minus n. Bilateral, definitely called bilateral because the lower limit there goes from minus infinity. So the bilateral transform, right? Bilateral has a lower limit of minus infinity rather than 0. We'll get a unilateral transform shortly, okay? So how can we start using this? Well, the transform offers us all the kind of advantages that a bilateral Laplace transform did, but usually we're not stuck in that transform domain. We usually have to get back to the time domain. So we do need to think a little bit about an inverse, what is called the inverse Z transform as well. So I'm going to go ahead and give this without proof. The mathematics here are a little outside of what's required for the prereqs in this class. Still informative, though, to think about what the structure of this is. So let's go ahead and do the inverse Z transform. This is a way to get back to a time domain signal. So I see I got my little h of n, right? And it's going to have a complex constant out here. We don't have to worry too much about that. So it's a 1 over 2 pi j. And then I'm going to get an integral, and we're going to come back to that. It might surprise some of you that it's an integral, but it definitely is an integral. There's a little circle on here, so it's a closed contour integral. Again, we don't have to worry too much. Just think of it as an integral. And then I've got that frequency domain or transform domain, h of z signal, and it's going to get multiplied by a z to the n minus 1, and then there's this dz element. So this is the form for the inverse Z transform. Let's make a little bit of a kind of a story behind this one, just like we've been doing in the past. So what does this really tell us? It tells me that we have a discrete time signal, right? We have some discrete time signal, and it is, that's the equal sign, right? It is a sum, so that integral, even though it's a closed contour integral, it's still a limited sum, if you will. So it's a sum of, and that h of z is just a bunch of scale factors, so it's some scaled. And then if we look at that z to the minus n, those are complex exponentials, right? Complex exponentials. So what is this Z transform all about? Or if you look at the inverse Z transform, what is it telling us about? It's a way of saying that we can generate a discrete time signal and represent it in a different way, right? So it is just a sum of scaled complex exponentials. If you think about Taylor said you could have a signal and it's represented as a sum of polynomial pieces, scaled polynomial pieces, for example. Taylor is useful in some particular cases because polynomials have some useful properties under certain operations like integration or differentiation. In the same way, this inverse Z transform equation, this synthesis equation as it's called, this synthesis equation has some utility too. It says that discrete time signal, right, is a sum of scaled and complex exponentials. Why do we like to break it up in terms of complex exponentials? Because we know complex exponentials have really easy characteristics going through a system, right? We solved that problem up here. We had a complex exponential in, and it gave us that same complex exponential out, multiplied by a complex factor. No convolution, nothing like that. It just became multiplication. Convolution became multiplication. Very, very nice result. We like exponentials on systems because they're easy. So this inverse Z transform says, hey, let's make sure that we can break up a signal. Let's represent it in terms of scaled and summed up exponentials, because exponentials are easy. The summing and scaling is just connected to that linearity property. Sums and scales of inputs would give us sums and scales of outputs. We've seen that kind of property before. So linear combinations of these convenient functions, really, really nice. So I think this equation here, the story behind the equation, is a good one. Discrete time signals are a sum of scaled complex exponentials. Probably not so easy to evaluate, and it really comes down to, much like in the Laplace case, because of that differential element. In this particular case, we see the differential element is dz. Z is a complex variable, so this is integration with respect to a complex variable. It's not your normal calculus. You need some complex variable theory in order to carry that guy out. Instead, we're going to do things through tables and partial fraction expansions. That's sort of an idea, just like we did in Laplace. But the story behind this also just very useful. Just as a quick reminder, if you took a look at the continuous time case, we had the inverse Laplace transform, right? That inverse Laplace transform ended up having a very, very similar kind of structure in here. If we take a look at that particular guy, really, I think, pretty easy to do. We can take a look at this guy, and it's going to have that same sort of complex factor up front. It's a 1 over 2 pi j. We have an integral. It's a line integral, so it goes from some c minus j infinity to some c plus j infinity. C just tells us kind of where along the real axis we're going to be integrating. And then I have my h of s, and I have an e to the st ds. So Same sort of story, right? A time domain signal is represented as a sum of scaled complex exponentials, just like what the inverse Z transform told us. Same exact kind of structure, a little bit of difference in exactly where we're integrating in the complex plane. It was hard again too because of that differential element being with respect to the complex variable Z or S, complex variable S. And that's just not something that we have the background prereq requirements for in this class. Okay, so we can go back to where we had gotten. We have this idea that I can get to the transform domain h of z by taking the forward z transform. That's a summation on my independent time variable n of my signal h of n weighted by these exponentials z to the minus n. And I know that I can get back, at least in theory, to my time domain signal h of n as, well, there's a little old scale factor out here, 1 over 2 pi j. I've got a contour integral sitting in here. And then I've got my h of z, right? And I have my z to the n minus 1 dz. Very, very similar structure as what we saw in the case of Laplace transforms. Okay, so let's work on some intuition. We've got the bilateral transform equation sitting in here. The first one, if you remember, this is the bilateral z. So bilateral z transform. And the other one is the inverse z transform, inverse bilateral z transform, which we will do by tables and partial fraction expansion, as we talked about before. I'd like to work on some intuition. So let's think a little bit about intuition with regard to the frequency variables. I think it's worth some time thinking about how the frequency variables for a continuous time signal and those for a discrete time signal are different. So let's start in Laplace because we'd spent a bunch of time over in Laplace. So I'm going to be looking at Laplace. We know for Laplace, the frequency variable is this variable S, right? So S is our idea of complex frequency. So when we do a Laplace transform, it's seeing the complex frequency content, right, of our time domain signal. And if we think about that S, we oftentimes wrote it in a rectangular form, sigma plus j omega. And we know that S really, when we think about that frequency, it was all in terms of that everlasting exponential e to the st, right? So e to the st, the complex frequency S, has meaning or it has sense, right, in terms of this exponential e to the st. If I think about letting that variable s equal sigma plus j omega, sigma is like our damping factor again, right? If sigma is greater than 0, the thing grows. If it's less than 0, it decays. If sigma equals 0, that means we're right on the imaginary axis. That's just going to have oscillation. The variable little omega is just my radian frequency, so rads per second, and it tells me the oscillatory component in here. We've seen all of that. If I let sigma equal 0, right, then I would get an S equals 0 plus j omega. That damping factor now is neither damping nor growing. It's just a constant envelope, and we get purely oscillatory components or purely oscillatory behavior. And so this is going to give me an exponential that looks like an e to the j omega t. If I break that out by Euler's form, I'd get a cosine omega t plus j sine omega t. Neither of those have a growth or a decay component on them. So this is that oscillatory behavior. If we look at e to the j omega t, we'd seen this before back in the background chapter. That's just a unit length vector in the complex plane that's rotating counterclockwise according to the speed omega. And we know that if we looked at just the real part of it, it would give a sinusoid, a cosine kind of oscillation. And if I looked at the imaginary part, I'd have the quadrature or 90-degree out of phase component, the sine piece. So it's all harmonic motion, kind of motion of rotation sitting on in there. If I think about that omega then, right, that omega tells me the frequency, and I'm going to do a very quick sketch of this S-plane, the complex frequency plane. We've looked at this before, so here's our S-plane, right, the complex frequency plane. I know that I have the real part of S, that's the sigma, right, along the horizontal, and I've got the imaginary omega along the vertical. So when I let S equal j omega, when I set that real part equal to 0, what that is really doing, right, if I take a look at where that is in the complex plane, it's right there along the omega axis, right? So in this case, when S equals j omega, that in the complex frequency plane is right along that imaginary axis, along the omega axis. If I wanted to think about some points of interest in this particular case, I could look right there at the origin, right? That is S equaling 0. If I looked at e to the 0t, the corresponding frequency, that's just 1, that's DC. So S equaling 0, this whole piece is where DC is. DC is just one form of sinusoid. And as I move away from DC, as I go up or down the omega axis, right, I'm increasing my little omega. That's increasing the frequency, the rate of oscillation. And I can do that forever. I could keep going down or I could keep going up forever. I can make those oscillations as big or as small as I want. That's just one of the characteristics of a continuous time. So now we'll take a look at the discrete variable case, discrete frequency. So we know in discrete case, we're using the discrete frequency, complex frequency Z. So Z is our idea of complex frequency, just like S was our complex frequency for continuous time. We interpret this a little different though. We know that the convenient form for complex exponentials for discrete time is of the form Z to the n. It's not e to the something, it's Z to the n. If I go ahead and write Z in its polar form, I get an R e to the j omega, and we can raise that to the n, and that exponential then is an R to the n e to the j omega n. So the complex frequency Z has a damping factor R that tells us whether the exponential is growing or decaying, and it has a frequency kappa omega, kind of like little omega. Its units are radians per sample, and it tells us how things are oscillating. So we're going to have to interpret Z just a little bit different than we did in continuous time. If we go back up to continuous time, we had seen before that we had S as being the complex frequency. We wrote it in rectangular form, sigma plus j omega, and we recognized that it had that complex exponential form e to the st. We found that sinusoids lived where there was no damping, right, no exponential growth. We're interested in the same point here for discrete time. So in order to make this guy, the z to the n, not grow, we need the norm of z to be equal to 1, which really just says that we need r, our parameter r equaling to 1. In that particular case, then z to the n, when we have norm z equaling r equaling 1, we know this thing is just purely oscillatory, e to the j omega n. That's where sinusoids are. Sinusoids for the z variable live when r equals 1, norm z equaling 1. I'm going to go ahead and look in the complex z-plane then, complex frequency plane for discrete variables. So we've got our z-plane in here. We could still look at the horizontal axis as being the real part of z, and the imaginary axis as being the imaginary part of z, something along those lines. And what do we know? In polar form, r just tells us the distance from the origin. So if we're fixing that to be 1, we're looking at the unit circle. So sinusoids in the z-plane, right? This whole thing is the z-plane. Sinusoids in the z-plane lie on that unit circle. So I could look at that unit circle. That's where sinusoids live. So sinusoids live on the norm z equaling r equaling 1, right? When we've got that non-damping, non-growing kind of case. A couple of cases that are pretty easy to look at would be, for example, z equaling 1. So if I go z equaling 1, and we could think of that as e to the j0 with a radius of 1, again, something like that. Then if I have z to the n, that's 1 to the n, which is just 1. That's DC, right? And if we think about that in terms of the digital frequency, kappa omega, that's kappa omega equaling 0. So when we think of this point z equaling 1, frequency omega equaling 0, and we want to locate that in the complex z-plane, we see that it's right there at z equaling 1. It is on the unit circle. It is a sinusoid. DC is a sinusoid. It's the lowest frequency sinusoid. So the z equaling 1 is our DC point. If you remember back in the S-plane, DC was at the origin. In the Z-plane, DC is at z equaling 1. It's on the unit circle, not at the origin. If we wanted to, we could move away from DC. We would increase our frequency. As long as we stay on the unit circle, we're doing that as a sinusoid. So we can move away and we should be able to get higher and higher frequency. If I keep moving away and keep moving away, eventually I'm going to come over here to Z equaling 1 with a minus sign. So Z equaling -1. That thing should be high frequency. That should be some sort of high frequency. It is the farthest we can get away while staying on the unit circle away from the DC point. If I kept continuing past that, you'll see that I actually start making my way then back towards DC. There's a kind of a strange phenomenon going here. We keep increasing frequency and all of a sudden the oscillations start decreasing. We become more slowly oscillating rather than going faster. This we're going to find out is a phenomenon called aliasing, and it's a quirk of discrete time. It's something we need to get a handle on. Let's first take a look at that Z equaling -1. So if I take a look at Z equaling -1, put that into polar form, that's 1 e to the j pi. So here we're talking about a kappa omega equaling pi, a digital frequency equaling pi. If I have my z to the n now, that's going to be e to the j pi n. Break that up using Euler's. I'm going to have cosine pi n, and I'm going to have a plus j sine pi n, something along those lines. Sine pi n is always 0, so we don't have to worry about that term, and we end up just with cosine pi n, something along those lines. Let me get that correct. If I take a look at different values of n and the corresponding values of cosine pi n, we do get confirmation that this is that high frequency component. So let's look at 0, 1, 2, 3, 4, and so forth for n. Cosine of 0 is just 1. If I put in n equals 1, I get cosine of pi, that's -1. Cosine of 2 pi, that's 1. Cosine of 3 pi is -1. Cosine of 4 pi is 1, and so forth. So this is a repeating pattern. It goes from 1, right, to -1, to 1, to -1, to 1. It sits there and oscillates between the two extremes as quickly as you possibly can in a discrete time. From one sample to the next, it jumps between the two extremes. That's as fast as it can possibly get. Why, though, we might ask, is it that if I double the frequency again, we were just looking at the particular case here, kappa omega equaling pi. If I doubled that, so if I did 2 times that, right, I would get a new frequency, let's call that omega prime, equaling to 2 pi. You would think that doubling the frequency would double the rate of oscillation. Of course, if we throw that in, we would have an e to the j2 pi. Go ahead and raise that to the n. That's going to be e to the, well, what is e to the j2 pi? E to the j2 pi we know is 1, so that's 1 to the n, which just gives us 1. That's back to DC. That is confirmed over here on our frequency plot. Let me go ahead and put this in red. If I started out at DC, we know where that is. That's omega equaling 0. I can move over here pi rads per second. So if I get over here to high frequency, right, that one there is at omega equaling pi. Now I double it again. I keep moving. I'm going to go through another pi. It puts me right back at DC. So doubled the frequency in this particular case, but because I started heading back to the DC point, I found out that instead of increasing rate of oscillation, I actually decreased it. We'll be able to answer this with some other pictures and thinking about this phenomenon called aliasing. We certainly see how the math works here. If I have this doubled frequency being 2 pi, I put it into the exponential form, I find out that I just get out that DC1. So what's going on? Well, some pictures I think can help us out. I'm going to start by taking a look at, let's actually write out the equation first. Let's think of taking a continuous time sinusoid. I'm going to call it cosine omega t. We all know about sinusoids, something along those lines, and I want to sample that guy. So I'm going to sample that, sample at some uniform rate. So I'll go ahead and sample this thing at a uniform rate of n cap t. So every cap t, I'm going to take a new sample. So if I go ahead and do that, if I do that sampling on there, I'll get a digital sinusoid, cosine, and omega 4 times t equaling n cap t, which I could write out as a cosine, and I could have here omega t times n. Well, that right there we could call my cap omega. So this would give me my digital sinusoid cap omega n, something along those lines. So we get this idea that our digital frequency, if it was uniformly sampled, is connected to our continuous time frequency, little omega, through the sampling interval cap t. For simplicity in this particular case, so for convenience, for convenience, let's go ahead and set cap t equaling 1. What does that mean? It means I'm going to sample once every second. I'm going to start out by looking at a little omega equaling 0. That's a DC signal. Let's go ahead and draw that. So I'm going to go ahead and give my axis here. Here's some different values of time. I'm going to go ahead and give myself the vertical axis, and I just have that DC value of 1, something like that. If I sample at t equaling 1, so let's go ahead and think about that. So I'm doing this at t equaling 1. I'm going to do this in a different color. So at 0, and at 1, and at 2, and at 3, and at 4, and at 5, each one of these things, right, is separated by t equaling 1. I'm going to sample this continuous waveform. So I'm going to go ahead and get my first sample, and I'm going to get my second sample, and I'm going to get my third, and keep going on. And what I see is that DC continuous time signal stays DC for my discrete time signal. Cap omega in this case is equal to 0, coming from little omega equaling 0. Why? Because we know cap omega equals little omega t, with t equaling 1. I'm just going to get this in this particular case equal to little omega times 1, or just little omega. So if little omega is 0, cap omega equals 0. DC goes to DC, just as we would hope. We're going to now move to a case of a little bit higher frequency in here. I'm going to think of something that takes 2 seconds to oscillate. And so in that particular case, I could sit there and think about it. Its Hertzian frequency is a half. Its radian frequency is going to be pi, something along those lines. And so in this particular case, I'm going to be talking about a cosine of pi t. And if I take a look at that particular one again, so I'm going to go ahead and draw my axis in here. We know that at 2 seconds and at 4 seconds, every 2 seconds, it's gonna repeat. It's a half Hertz waveform, so it takes 2 seconds to complete a cycle. So I'm going to go ahead and draw that in there. So there's 1 cycle in there, and there is 2 cycles, and I'm not doing such a great job of making this beautiful, but you get the idea. So that would be this cosine of pi n. If I go ahead and sample this guy, same sampling interval, t equals 1 second, what do I find out? I end up getting a 1 at 0. I'm going to get a minus 1 at 1. At 2, I go back to that value 1, and then minus 1, and then 1, and minus 1, something like that. So this was, again, sampling using cap t equaling 1. My sampled signal then is going to be cosine omega little nt, t though is 1 in this case, right? Which just in this case, because a little omega is pi and my cap t is 1, I'm going to get cosine of pi, and cap omega again equals little omega, so pi equaling pi. So this cap omega equaling pi, that's what we determined was that high frequency case. So this was the high frequency case. Should have been the highest frequency if we went back to the z-plane where we were trying to visualize where all these frequencies were. If you remember DC, this cap omega equaling 0, that was right here, cap omega equaling 0. We had this other one over here. This is cap omega equaling pi. That's that high frequency, as far away from DC as we can get. We come back here and we get exactly what we would expect, a really high rate of oscillation. It goes from a 1, and then it goes back down to a minus 1, and a 1, and a minus 1, 1, and minus 1. It's sitting there oscillating as fast as it possibly can as a discrete signal, cap omega equaling pi. So we're going to double the frequency again, right? This double frequency again should give us a cosine of 2 pi t. So pi became 2 pi. Sample that again at a t equaling 1 sample rate. We're going to get a cosine 2 pi, right? So 2 pi, t is now n cap t, but cap t is 1, so it's a 2 pi cap, 2 pi n. It gives me cap omega equaling 2 pi. So double from what we previously saw. Previously saw cap omega equaling pi being very high frequency. Here we've doubled it again. If it happened like a continuous time sinusoid, it would have gotten much higher in frequency. The period would have shrunk. We can get a visual of this. Let's go ahead and draw it out. So we are going to take a look at a graph here. Things are happening now on 1 second intervals. So we've got 1 in here, 2, 3, and 4, or something like that. The continuous waveform, what do we have? We have 1 period per second. It's a 1 Hertz waveform. That means we're going to get 2 periods over 2, and a 3rd period over 3, and a 4th period over 4, something along those lines. So if you take a look at that continuous time waveform and you compare it to the one we had before, The other one took a total of 2 seconds, right? So we had 2 seconds for its period. We doubled the frequency that halved the period. So this one has a period of 1 second, something along those lines. It's certainly oscillating faster, twice as fast. But now what happens when we actually sample this guy? We sample it, again, we're still sampling at 1 second. So we come in here at 0, we get a sample. 1, we get a sample, which also happens to be 1. 2, we get a sample of 1. 3, we get a sample of 1. And 4, we get a sample of 1. All of those samples end up giving us the same value, giving me this idea that this digital signal looks DC. That's the aliasing that goes on. Aliasing here is where a high frequency continuous sinusoid ends up looking lower frequency because our sample rate is just not quick enough to keep up with the oscillations of the waveform. So going back to our overall frequencies here, right, if we look back at where frequencies live, we already have this idea. I'm going to change my color again just so we can get an idea of where I'm at. DC, right, is sitting there. We move away from DC, so omega is increasing until I hit omega equaling pi. That's high frequency. If I keep moving and continue on, right, it ends up slowing down because we've aliased. The second we pass that point, omega equaling pi, we start getting slower, and it's going to seem slower until we hit that DC. If we kept continuing, we could come around again and we could eventually hit a high one again. So this would be the same as 3 pi, something along those lines. And then 4 pi would bring us back to 0 again. And it goes on in an infinite loop. Anything outside that principal range, plus or minus pi, is an aliased signal. It's where that continuous type waveform is oscillating too quick for the sample frequency. We are not capturing all the detail that's going on in this guy, right? So this guy's oscillating, and yet we get samples that don't show any oscillation whatsoever. We just aren't sampling fast enough. This gives us a basic kind of an idea, right? That really you need to have an underlying sample rate that is quick enough that it can capture all of those oscillations. We can derive that out to being twice, sampling twice the highest frequency. We'll do that a little later. Okay, I think we're ready for a bit of a transition now. What have we done up to this point? We've introduced the bilateral Z transform. We took a look at it in terms of its forward transform, right? That gave us that H of Z. We also looked at the inverse Z transform. That's this idea that any old time domain signal can be represented as a sum of scaled exponentials, something convenient for signals. We've been working on some intuition about the frequency variables. Both Laplace and Z have a complex frequency variable. Laplace has S, Z has, well, the Z variable. They are interpreted a little different, and looking in either the S-plane or the Z-plane is different. Sinusoids, if you look at where sinusoids live, fundamentally different. For the S-plane, it's along the omega axis. For the Z-plane, it's on the unit circle. Almost always when you're doing a Z-plane plot, you're going to want to put the unit circle for reference, just to give us that idea of where sinusoids live. What we'd like to do now is we want to go ahead and think about how we're going to compute out. So we're going to do a couple of cases of computing the bilateral Z transform. So we're going to go ahead and do this bilateral Z transform. We'd like to do a few cases of this, see what it looks like, try to mechanically go through it. I'm going to pick 2 particular cases that are going to be very similar to what we did in continuous time. But before we get to that, I just at least want to talk about this idea of convergence. We had a convergence idea in continuous time when we did the continuous transform, the bilateral Laplace transform. We knew that the transform had to converge in order to be useful. We're going to need the same kind of condition here for discrete time. To be useful, the Z transform has to converge. It can't go off to infinity. So let's talk a little bit about convergence ideas. Let's talk a little bit about convergence ideas in this particular case. So a necessary, so I'm going to look at, in this case, a necessary condition, a necessary condition for convergence. Convergence is this idea of absolute summability, something like that. The Z transform we know is a summation from n equals minus infinity to infinity of x of n, right? Z to the minus n. That is just the definition of the Z transform. I want to know that the magnitude of this guy is well behaved. And so I'm going to look at the magnitude of that sum. We know from the triangle inequality, we'd seen this before, that's always less than or equal to the sum of the magnitude. So the sum from minus infinity to infinity of the magnitude x of n r to the minus n and e to the minus j omega n if I put it in the overall polar form for my z variable. And that whole piece there is equal to what? That's a summation from n equals minus infinity to infinity. And I'm going to have a norm of x of n r to the minus n, and I'm going to have a norm e to the minus j omega n, which is always 1, by the way, right? We know that that part is 1. So to converge, the only thing we have control over is the z, right? That's going to be the r and the omega, if you will. So to converge, we require, if I can get this spelled right, require an r such that this overall thing, right, this whole thing here ends up being a finite number. So we need this whole thing to be less than infinity. So everything about convergence is going to be based on r. Picking some value of r. We can set r to be big or small, and that's how we're going to establish the convergence. If you remember in Laplace, what we ended up playing with was we played with sigma, right? So for if we do just a little back reminder for the Laplace transform, right? The convergence idea had to do with the real part of S, which was the sigma. We looked at that guy and we did things like, is it greater than or less than some values, depending on whether the signal is right-sided or left-sided, something like that. Well, what was sigma? That was the damping factor. What is the damping factor for discrete time? It's R, so it's the exact same thing. Looks a little different. We know that the variables themselves are a little different, but they serve the same function. So we're looking on controlling that damping factor, if you will, that envelope. So I think the next examples are going to get to this. We're going to find out convergence for discrete time is going to be all about ensuring that we're in that part of the z-plane where the radius has a particular relationship greater than or less than some particular value. So instead of half planes to the right or left, right, we're going to be being on the interior of circles or the exterior of circles, looking at r being greater than or less than something. Those just describe circles. So let's try to bring this all together with a couple examples. So we'll go ahead and do this. The first Laplace transform example we did was a causal exponential. I'm going to do the same thing here, just discrete style. So x of n is equal to, let's say, an alpha to the n u of n. So causal because of the u of n, and the alpha to the n is just my exponential term. I'd like to go ahead and find the transform of this guy. So I'm going to go and take the x of z. That x of z is going to be a summation. We know that that's summing from minus infinity to infinity of my signal x of n, and I'm going to have that z to the minus n weight in there. Once I use the fact that this guy is causal, my sum limits are going to go from n equals 0 to infinity, and over that range I've just got that alpha to the n, and I have a z to the minus n, which is then going to be what? It's a sum 0 to infinity, and I can combine these two because they have the same exponent essentially. I'm going to have an alpha by z. Z to the minus 1 is just 1 over z, and that's going to be raised to the n. This is a geometric sum. We have talked about geometric sums before. We know that the geometric sum is going to go to, well, the ratio. This is alpha over z. Take the lower limit, that's 0, minus the ratio again, alpha over z. Raise it to the upper limit plus 1, so infinity plus 1 over 1 minus alpha over z. You can just look back in your notes and you'll see how we derived this result previously. So we want to get the overall transform here to converge, and I'm just going to say that this term out here is the one that's a little problematic because we've got that infinity term. It really only has a couple of choices. It can go off to infinity or it could go to 0. We want it to go to 0. So I want this term alpha over z, right, raised to the infinity plus 1 to go to 0. That way I'll get a convergent value for this transform. When does that happen? Well, we need the magnitude of alpha by z, right, to be less than 1. If I have a magnitude less than 1 raised to infinity, it goes to 0. This is going to give me a condition of norm z being greater than norm alpha. Norm z, by the way, is just what? That's just r. So that's where those discussions of convergence, when we talked about here, a necessary condition for convergence was absolute summability. We said something about it all involves this value r. Here it comes into play. We see it. It all came into this value r. We're bounding r so that it has to be greater than the size of that parameter alpha that was part of my signal, that thing that's the exponent base. Okay, so we have r greater than norm alpha. If that is the case, this is a condition, and we'll call this condition the region of convergence. So I'm going to abbreviate that just as I did in continuous time. My region of convergence is going to be norm z greater than norm alpha in this particular case. And if it is, then I can go back and I can write my x of z, and it's going to be equal to what? We're going to keep that first term, alpha by z to the 0. That's just a 1. The next term is going to be the one that converges to 0, so I'm going to get that 0 over 1 minus the ratio. So 1 minus, and the ratio here was alpha by z. Multiply top and bottom by z, and we get a little bit more nice form. We get z over z minus alpha. Let's clean this whole thing up and just remind us where we were at. We had a time domain signal x of n. It was an alpha to the nu of n. I did a bilateral z transform on that guy, so I took the z transform on that, and I found that x of z was equal to a z by z minus alpha with a region of convergence norm z greater than norm alpha, something like that. Something that you might notice here, if you remember when we were at continuous time, we had a continuous time signal, something like this. We had x of t equals what? We had something like an e to the lambda t u of t. When we Laplace transform that guy, we got a cap x of s as being equal to, in this particular case, we ended up with a 1 by s minus lambda, and the region of convergence in this particular case was what? It was sigma, which is the real part of s, and it had to be greater than the real part of lambda, something like that. So if we take a look at this, this is kind of interesting. The discrete time form, causal exponential, right, ends up going to a rational function in z, and it has a root. It has a root at, in this particular case, alpha. So if I was going to go ahead and plot that in the complex plane, I could just come in here and I would find some value. Let's just call this guy, and I'm going to make it a negative real number. I'm going to go ahead and make that my value alpha. It could be anything. It could be a complex number. It could be real. It could be positive, negative. Doesn't really matter. So I've got that guy. And the region of convergence here says that, hey, we can't include that. That's a pole in the denominator. If I used a value of z that equaled alpha, right? If I used a value of z that equaled alpha, my denominator would go to 0 and the overall x of z would go to infinity. That's not convergent behavior. So we cannot include this value of alpha in the region of convergence. So I'm going to put a little dotted line. It's a circle because we're interested in the radiuses. R is all about the convergence, right? And we have to go greater than, well, whatever the size or distance alpha is. And so I'm just going to go outside of that. We can always find these regions of convergence here just by plotting out where the pole of my signal is. This one down here, where we see the z minus alpha in the denominator, that's my pole. I have a pole then, right, sitting there at alpha over here in the complex plane z plot. We can't include that pole, and the region of convergence in this case is everything outside the circle that does not include that pole. Think about what it was for Laplace. We had a similar kind of thing, except for now it was the S-plane, right? That S-plane could have had some sort of root lambda. I'm going to just show it over here on the right. So here's my lambda, something like that. We knew that it could not include the region of convergence, could not include that pole. And we picked everything to the right of it, right? Instead of being outside of a circle, it was to the right of that guy. Very similar kind of thing. You can't include, right? We can't include poles in either case. You can't include the pole. It's just that the boundary for the region of convergence for Laplace was a straight line, and you look to the left or the right of it. Right if it was a right-sided signal, left if it was a left-sided signal. We've done this one now for the discrete time case. My boundary is not a straight line. It's a circle. That's not a surprise. Remember where sinusoids lived? They lived on the omega axis. That was this straight vertical line. Where do sinusoids live in discrete time? Well, that was that unit circle, right? This idea of region of convergence, it just parallels, it runs parallel. Circle is parallel to another circle, right? It runs parallel to that interior circle. These regions of convergence just mimic the shape of where our sinusoids live. So in this particular case, my region of convergence is the circle outside, right? The circle that bounds up against that pole location, something along those lines. Okay, so we've got it. This is one of our results, and we're going to go ahead and do this all over again, except for in this particular second example, much like I did for continuous time. I'm going to pick another discrete time exponential, but it's going to be an anti-causal one. So in this particular case, I'm going to go ahead and say y of n, and I'm going to let it be equal to, in this particular case, I'm going to let it be minus, and I'm going to do alpha to the n, and I'm going to do a u of minus n minus 1, something like that. This will look a little different. There are a few things that just are a little strange, like you get that minus 1 term there. That's related to this idea that individual points matter. We've made that comment many times. Basically, we can't repeat that DC, or not the DC, the n equals 0 point twice when we look at the causal and anti-causal parts on this. Let's go ahead and take a look at what that might look like in this particular case. If I go ahead and I draw my time domain signal, something like that, we're saying it's 0 for 0 and everything forward, right? And then it's going to have some exponential, like if alpha, for example, was a half, it'd be like a half to the n, and it's going to make this one, ooh, it would grow on an exponential envelope, and because of that minus sign, it would be looking like it would be growing towards minus infinity, something like that. And it keeps getting bigger and bigger and bigger as we went out. This particular case, right, has an alpha equaling like a half, something like that. If I looked at my previous example where I had x of n as being equal to alpha to the n u of n, same alpha, right? What would have it looked like? It would have been 0 everywhere before, and then it would have started something like a 1, and then it would have decayed down, something like that. Would have been this nice decaying exponential, causal decaying exponential. This other case y, right? This case of y of n is an anti-causal exponentially growing waveform, even though the alpha is the same. Very similar to the pair of cases I gave for continuous time. Anyway, we do want to go and try to find the transform of this, so I'm going to look at y of z. That's going to be a sum because it goes from minus infinity to minus 1, right? That's because of the u of minus n minus 1. It ends when n equals minus 1. That's the time I get this minus alpha to the n, and I weight that by a z to the minus n. Clean this up a little bit, I get a minus summation n equals minus infinity to minus 1, and I'm going to have an alpha by z to the n. I can go ahead and still recognize this as a geometric sum, so I'm going to have a minus sign out front. I'm going to have my alpha by z, right, to the lower limit, that's minus infinity, and I'm going to have a minus, and I'm going to have alpha by z to the upper limit, which was minus 1 plus 1, so I'm going to get minus 1 plus 1 is 0, and I'm going to have a 1 minus alpha by z, 1 minus the ratio in the denominator, something along those lines. What I need here, if you take a look at it, that infinity term again is the one that I'm worried about. To get convergence, that term has to go to 0. I can rewrite this. I can look at that alpha by z to the minus infinity as being a z by alpha to the infinity, right? Because I could write this alpha by z to the minus 1 as an alpha by z to the minus 1, then raise that to the infinity. And alpha by z to the minus 1 just gives me that alpha in the denominator, z in the numerator, so z by alpha raised to the infinity. Well, the way we get this to go to 0 is that this has to have norm z by alpha has to be less than 1. We still need that size less than 1. If you compute that out, that's norm z less than norm alpha. Just the opposite condition that we saw in the previous example. Previous example, right-sided signal gave me norm z greater than something. This left-sided signal gives me norm z less than something. Very similar to what we saw for the Laplace transform as well. So if that case is met, I end up getting my transform y of z being equal to, take a look up here, I had a minus sign, right? And that term converge because I'm in the region of convergence, 0, and I'm going to have a minus something to the 0, that's just a 1, and I have a 1 minus alpha by z. The minus signs cancel, and I end up with a 1 over 1 minus alpha by z, multiply top and bottom by z, I get z over z minus alpha. Let's clean this guy up. What do I get? I get y of z is being equal to z by z minus alpha with, right, a region of convergence, norm z less than norm alpha, something like that. In this particular case, then, if we take a look, we see again that the denominator here, right, has a root at alpha. So if I plot that out in the complex z-plane, I could go ahead and look at that root again there. There it is at alpha. I should have said root at alpha. Regions of convergence can never hold poles of a transform. That is a pole. The region of convergence boundary line is always circular. That's because it's based on that R that was connected to that region of convergence description we had before. Now, instead of looking outside, we're going to look inside. So my region of convergence is now on the inside. Inside circles, disks, regions of convergence that look like disks correspond to left-sided signals. Regions of convergence that look like the exterior of circles, like we had over here, correspond to right-sided signals. So it's a nice little memory, just like we had for Laplace. So let's do the final comparison here and finish this lecture up. So if you remember these particular examples here, I had example 1. In example 1, I had an x of n as being equal to an alpha to the n u of n, and we went ahead and z transformed that guy. I got not a y, I got an x of z being equal to z by z minus alpha with region of convergence norm z, right, greater than norm alpha, something like that. My example 2 was a y of n being equal to minus alpha to the n u of minus n minus 1. And when we went ahead and z transformed that guy, we ended up getting my y of z being equal to z by z minus alpha. And the region of convergence here was norm z, so I should probably call that a region of convergence, right? Norm z less than norm alpha. And I'll just go ahead and add that extra notation over on this other side, something like that. So this first one, z transform, a complete solution, would have both the x of z part and it would have the region of convergence part. Same sort of thing for my y1. I have the y of z part and I also have my region of convergence part. Let's do a very quick comparison of these guys. If you remember, and we could draw this out again just very quickly again. If you remember this first one, it was something like a causal decaying exponential of my alpha was something like 1/2, something like that, right? This other one was this sort of weird growing anti-causal signal, something like that. That was also alpha equaling 1/2, something like that. In this particular case, then, what do we get? We see that x of z and y of z are precisely the same thing. If we just said a transform was equal to z by z minus alpha, we wouldn't know if it looked like this decaying causal exponential or if it looked like this growing anti-causal exponential. The only thing that allows us to uniquely know that is the fact that we have further specified what this region of convergence is. Region of convergence, it's the exterior of a circle in this first case, right? That's a right-sided signal. That would mean I had this decaying exponential. Region of convergence, that's the interior of a circle, a disk, tells me that I have an anti-causal signal. So we must include the region of convergence to be complete in our transforms. Well, I think that's enough for this particular lecture. We'll pick it up next time.